This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's continue then. Maybe you can go down to the pad. Last time, right at the end, we looked at, well, this is what an exponential is. This is in fact, this is really what a matrix exponential is. Nothing but a time propagator in a continuous autonomous linear dynamical system. That's what it is. It is nothing else. So here's what it tells you. It says that to get the state at time tau plus t from the state at time tau, first of all, they're linearly related. That alone is, well, it's not unexpected. If they're linearly related, they're related by an n by n matrix that maps one to the other. And that matrix is simply e to the ta. So e to the ta is a time propagator. It propagates x dot equals ax forward t seconds in time. If t is negative, it actually runs time backwards and reconstructs what the state was some seconds ago. So we looked at that. Actually, that alone is enough for you to actually do a lot of very interesting things. And we'll look at a couple of examples here. One is sampling a continuous time system. Suppose we have x dot as ax. I have a bunch of times. We'll call these the sample times. And I'll let z of k be x of tk. So z of k is the sampled version of x at these sample times ti. The fact is, they just don't even have to be monotone increasing. It's totally irrelevant. Everything we're going to work out now has nothing to do with that. So the times can actually be, they can go backwards, and it makes no difference. Here's the important part. This says that to get z of k plus 1, which is x of tk plus 1, from x of z of k, which is x of tk, you simply multiply by e to the time difference times a. Okay? That's matrix exponential, of course, here. So this is what propagates you from tk to tk plus 1. If you have uniform sampling, then that says that the difference between these is some number h, which is the sample period. And basically you get this. You get z of k plus 1 is e to the ha z of k. And that's actually just, this is sometimes called the discretized version of this continuous time system. But this one is exact. There are no approximations of any kind here. This basically says, if you want to know how the state propagates forward h seconds into the future, you multiply by this constant matrix e to the ha. And that'll propagate you forward h seconds. So that's what this is. Okay. So there's a lot of things you can do that are interesting now. Here's one. These things really come up, actually, in lots of cases. So if you have a time-varying linear dynamical system, that's x dot equals a of t x. These do come up in some cases. It's much more common to find the time invariant case, but these do come up. And there's a bunch of things you need to understand about this. For example, the simple solution, which is a generalization of the solution of x dot equals little a of t x when these are scalars, is wrong. And I believe that's a problem on your current homework. Current homework? Oh, it is current. It's Thursday. I can say that. I forgot to announce that. We did post homework 6. And not only that, there's an M file, which you can actually get to now, that AFS has graced itself, graced us with its presence yet again. So we've assigned homework 6. Homework 5 is still pending or something like that. I think originally we said it was due Monday or something, and we decided that was weird. So it's just due Tuesday. Is that how it all converged? It's due Tuesday. It was never due Monday. Well, okay, fine. Like I said, don't trust me. I used to say trust the website. That's why it was so upsetting when it was gone this morning. But it didn't bother any of you, right? Did it actually? How many people here actually even noticed it? When? This morning. Okay, because we were mucking around at around 11 or midnight or something, and it was fine. So, did it bother you? You're like totally cool about it? You're like, no problem, it's just not there. You must have done it right before class. Okay. Jacob was doing the following. He did the same thing, rather. He was fiddling around. It wasn't there. He did something. It was there. And he said, I fixed it. I think. He may have. We don't know. Anyway, it's back. So, okay. Back to piecewise constant systems. Okay, so here, if you have a piecewise constant system, it means that the dynamics matrix here is constant for certain periods of time. These come up all the time. Oh, by the way, there's a wonderful name for this. This is called sometimes a jump linear system is one name for it. And before we get into how you analyze them, I'll just give you an example. So a very good example that I know about or heard about is people working on, for example, power systems would be one. So a very good model, for at least for small perturbations in a power distribution network, is linear. Actually, that's not a good model for huge perturbations, but for small ones, very good model. And what happens is people will analyze something like this. A0 will sort of be the nominal dynamics, the dynamics of the system when everything's working. So the state is kind of, presumably going to 0. That's what 0 means everything's, everything's the way it should be. That 0 means all the phases are in line or whatever they're supposed to be, like this. Then what happens is at some time, and that might be called something like TF for fault time. So at TF, basically some, lightning strikes or something happens, and some circuit breaker, for example, shorts or something like, some line shorts. There's an overcurrent situation. And then they have another name, I remember this, is TC, which is the clearing time. The clearing time means that a breaker opens now. Now, by the way, then you would have things like, a nom would be the original dynamics matrix. That's when everything's cool. Then you'd have AF. That's the dynamics matrix when this short is there. Then you'd have AC is a different matrix still, which is the dynamics matrix when the circuit breaker is opened. Something like that. And so you want to ask questions now about what happens to the state in this time-varying linear system. You might ask, for example, how big does the state get? One hopes that it then gets smaller again. And we can answer it this way. So these are the types of questions you can answer. You can do studies where you could say, well, if the circuit breakers open in 5 cycles, maximum, what happens? What if that were 3? What if it were 7? How much trouble can the Western U.S. grid get into? And these would be the kind of the questions, the types of things you could answer. Okay, that's just an example. Let's see how this works. So to get the state at a given time, here's what you do from the initial state. You start with the initial state, and you propagate it forward t1 seconds in time. What is the stuff between my fingers there? What's that? That's x of t1, because we just propagated it forward. Now, by the way, if someone says, well, wait a minute, you're using a matrix exponential. This is a time-varying system. Everyone knows you can't use matrix exponentials for a time-varying system. What would you say? Thank you. You'd say, that's true. But over the interval 0, t1, it's a time-invariant system. The matrix A does not change. Okay? Now you take this matrix, which is x of t1, and you propagate it forward t2 minus t1 seconds, and what does this give you? That's x of t2. And you keep going until the last instant before t occurred, and then you propagate forward the remaining time. That's this. Okay? So this is the picture. And you should read that exactly that way. I mean, when you see it, you should know what every single piece is and so on. Okay. So this, by the way, this matrix here is called, that is actually called the state transition matrix for the time-varying system. And in fact, some people write it this way, phi of t and 0, meaning it is the matrix that propagates x of 0 into x of t. Okay, so that's the name for that. Okay. So we can also analyze things like the qualitative behavior of x of t. This will actually make a connection to things you know from undergraduate and scalar stuff. So let's take x dot equals ax like this. Then x of t is e to the ta times x of 0. The Laplace transform of x is this resolvent, si minus a inverse times x of 0. Now, every component of the state Laplace transform is an entry of this, but each one of these looks like this. Every entry of this matrix is a rational function with a numerator of degree less than n, a denominator, which is exactly n, multiplied by then some numbers here. So the result is each of these entries in this Laplace transform of this state vector is a polynomial of degree less than n divided by the characteristic polynomial. Okay? Now, this is just a scalar, and we know a lot about the qualitative behavior of a function like little xi of t based on its Laplace transform here. So what you see here is that the only poles that capital Xi of S can have are the eigenvalues of A. So that tells you that the only terms you're going to see when you work out the solution, right? And well, I guess we'll first assume the eigenvalues are distinct. That's the simple case. Then the solution looks like this, of course. It's simply a sum of exponentials. Now, these can be complex here. Okay? So in this case, you get a sum of exponentials. And the exponentials here determine, of course, the qualitative behavior. But these exponentials here are the eigenvalues of A. So what that means is the following. The eigenvalues of the matrix A give you the exponents that can, and I'm going to emphasize, that's not can, it is not do, it's can occur in exponentials. Okay? And the reason it's not do is that some of these betas can be 0. Okay? A real eigenvalue, of course, it corresponds to either an exponentially decaying or a growing term. And if it's either exponentially decaying, if it's negative, or it's growing. A complex eigenvalue corresponds to a decaying or growing sinusoidal term. So now at this point, you can say that you know qualitatively what all solutions of x dot equals ax look like. And here's the cool part. It's no different. What's interesting about it is this. You know already that you get much different behavior in a matrix, a vector linear differential equation than a scalar one. In a scalar one, the only thing you can have is exponential growth or decay. That's it. Here, we've already seen weird stuff. We've seen oscillations. We've seen things growing like t, not exponentially. So we've seen some pretty weird stuff. And you ask the question, how weird can it be? Now we know the answer. The answer is, we'll get to the t's later. But for the moment, it says that basically the solutions of x dot equals ax, if the eigenvalues are distinct, basically are damped or growing sinusoids. They're exponentials multiplied by sinusoids. And you know what that is, by the way? That's this. It's this. It's well, I'll put it all together. It doesn't matter. So what it basically says is that the types of behavior you see in second order linear differential equations, or scalar second order differential equations, because these equations, of course, will give you exponentials multiplied by sinusoids. And it basically says that's it. So you're not going to see anything different from second order systems like that. That's not quite true. But for the moment it is, as long as the lambda are distinct. Okay? So that's what that says. Okay. So you get a famous picture, which you've probably seen. I don't mind showing it again. It's something like this. If you plot the eigenvalues of the matrix in the complex plane, they occur in complex pairs. In other words, whenever something is here, its conjugate is here as well, like that. And this tells you something immediately. If the eigenvalues, oh, by the way, what's the size of the matrix here in this case? What's the size of A? 6 by 6. So it's a 6 by 6 matrix. Here are the 6 eigenvalues. And it says that if these are the eigenvalues of A, it says that when we look at the solutions, we should expect a growing exponential here, with actually that grows at a rate given by that. This is sort of an oscillating, this one gives you an oscillating solution that's oscillating but also decaying. And these things are just rapidly decaying things. That's rapidly decaying. By the way, this one is a decaying exponential. Would you see a decaying exponential multiplied by a sinusoid? By the way, for this one, if I showed it to you, would the oscillations scream out at you? No, you wouldn't even see it. You'd be hard-pressed to say it oscillates. And the reason is, although the solution looks like e to the minus sigma t, e to the minus sigma t times cosine omega t, something like that, it turns out e to the minus sigma t has already gone down by some huge factor by the time one cycle has gone over. So technically, the term associated with this goes through infinitely number of zero crossings. You won't see it. So for all practical purposes, this thing would just look like a bump, sort of something that goes like that and down. So, okay. All right. So that's the picture. All right. Now, let's suppose that A has repeated eigenvalues. Now we'll do the complicated case. In this case, the Laplace transform could have repeated poles. By the way, it might not. And soon we'll see exactly what that means. So if you write the eigenvalues as lambda 1 through lambda r, and these are distinct with multiplicities n1 through nr, so these add up to n, then x looks like this. The solution is the inverse Laplace transform of a rational function with repeated poles. And those look like this. It's an exponential that's complex, so that's both got a sinusoidal term and a decay or growth rate factor, exponential, multiplied by a polynomial. Now actually you've seen everything. So you get, and now you remember one of our examples we saw before was a system where the solution actually grew like t, right? And that's exactly this, where that's where lambda was 0 and you had a t in here. So that's all that is. Okay, so that's basically it. That's the only kind of solutions you can see for x dot equals ax. That's the whole story, qualitatively. Okay, so we can answer a very basic question, which is stability. So it's a very old term. Actually, in some ways, it even started a lot of the study of this. I'll say why in a minute. So you say that x dot equals ax is stable if the exponential, if this matrix exponential or state transition matrix goes to 0 as t goes to infinity. And let me just quick syntax scan check. What's the size of 0 here? What is it? It's n by n. That's a 0 matrix. That says if every entry of this exponential goes to 0. Now that has a meaning that basically says this. It says that since x of t is this matrix times that, if every entry of this matrix goes to 0 as t goes to infinity, it says that no matter what x of 0 is, x of t goes to 0, period. That's what it says. Another way to say that, I guess it's the same story, but it's in a more flowery language or something. It says that basically any solution of x dot equals ax, there's lots of them, and all of them have the property that as t goes to 0, x goes to 0. So all trajectories converge to 0. Okay? So that's stable. Now there are, you will hear other definitions of stable, often, hopefully, with some qualifier in front. Just ignore them. So that's my advice, because they're silly, and you'll hear things like neutrally stable and anyway, just not only ignore the terms, but avoid those people. They just make things complicated when they don't need to be. So it's not good enough just to have one idea of like stability, so they have to have 14 different ones. Okay, so they can hold forth about when one implies the other. All right. So we can now say when this occurs. It's very simple. You can say x dot equals x stable if and only if all the eigenvalues of A have negative real part. We'll get the only if part actually later today, but the if part we can get right now. Actually, how do you know that? I mean, it's simple. Every solution looks like this. It looks like a polynomial times e to the lambda t. If the real part of lambda is negative, e to the lambda t here, it's a complex number, it sure goes to 0 as t goes to infinity. Actually, it doesn't matter what the order of t is, because an exponential will eventually swamp out any polynomial. Okay, so you get 0. The only if we'll get very soon. But in fact, this is very, very unsophisticated. This is very qualitative to say stability. So for example, already much more interesting and much more useful is the following observation. If you take the maximum of the real part of the eigenvalues of a matrix, it actually tells you the maximum asymptotic logarithmic growth rate of x of t. If it's positive, if it's negative, it tells you that. So merely saying stability is pretty much totally of no interest. You know, it's qualitative, it has no use. So if you're designing something, if you're designing some kind of protocol that you know, where a filter or a control system or something like that, and you come back and you say, that's it, I'm done. They say, yeah, and they go, well, yeah, how does the aerodynamics work? And the aerodynamics might be, X might describe some error that you're trying to drive to zero, and you say, oh, it's stable. Yep, it's stable. But that's of no practical interest. There's no practical situation where mere stability is of interest. It's of no interest whatsoever. You have to ask the time scale in which it's stable. If you make an altitude hold controller and the aerodynamics is stable, but the smallest eigenvalue is just barely less than zero, so that basically on an entire flight you won't have actually converged to your altitude, it's not relevant. So, I might add that goes the other way around. So I remember talking to some people once, and I remember asking about stability, and they're like, no, we don't. But I have to tell you what they did. They made missiles. And I said, well, what, you know, I remember someone asking something about stability, and they said, stability? What's that? We're like, well, surely the error as this thing moves can't diverge. And he goes, why not? He said, these things they have 10 seconds worth of fuel. We don't care. All we care about is that e to the ta, which would magnify an initial error. E to the ta times an initial error should not be too big when t equals 10. So they said we couldn't care less. There's other cases actually where you have that. No, I wasn't working with them. Is that what you're thinking? I can tell. I wouldn't do that. Okay. Okay. Now we're going to actually tie this all to linear algebra, which is kind of the cool part. This should be review, I guess, for, you've probably seen all this. I guess, how many people have actually heard about eigenvalues and eigenvectors or whatever? So, and in how many cases was the discussion comprehensible? Cool, great. Where was that? That part? You mean just compared to the rest of the class, which was abysmal? I mean, did they actually say what eigenvalues and eigenvectors meant? No, okay, anybody can say that. I mean, that's, here, det si minus a is 0. Okay, there, I just said it. No. I mean, like, do you have a feel for it? Yeah, okay, so that's the classical one. And for the record, that was the good experience. No one else raised their hand. So, okay, all right. That's fine. That's, okay. We'll fix that. So, a complex number is an eigenvalue if det lambda I minus a is 0. I mean, that's the same as saying lambda I minus a, which is a square matrix, of course, is singular. Lots of ways to say that. Of course, an n by, you know, a matrix is singular if it has a non-zero element in the null space. That means lambda I minus a times v is 0. If you work this out, that's lambda I times v equals a times v. That's av equals lambda v. Like that. By the way, later we're going to see there's a really good reason to write this as AV equals V lambda. Even though that's slang, but there's a way in which this is slightly cooler. But we'll get to that later. But it's traditional to write AV equals lambda V. Okay. Now, any V that satisfies AV equals lambda V and is non-zero is called an eigenvector of A associated with eigenvalue lambda. So that's what you call that. And obviously, if you have an eigenvector, you can multiply it by 3 or minus 7, and it's still an eigenvector. And in fact, these are complex, so I could multiply. They may be complex. I can multiply v by, you know, minus 3 plus j, which is I. So, okay. Now, another way to say that this matrix is singular, lambda I minus a, is to say the following. It's to say that it has a left eigenvector. This is essentially saying that the rows are dependent. Sorry, this is the columns. This says that the rows of lambda I minus a. Now, this, if you expand this out, says W transpose A equals lambda W transpose. And, oh, by the way, what is the dimension? What equals is that? It's equals between what? Row vectors, exactly. 1 by n matrices are row vectors here. Some people write this around the other way. They write it A transpose W equals lambda W. There, they write it that way. So in fact, you can see now that this is, in this case, this is the eigenvector equation, right eigenvector equation for the transpose. So if you have something that satisfies this, it's a left eigenvector of A. And actually, how many people heard about left eigenvectors? Cool. No one. Fine. Good. You didn't hear about it and you're just like holding back or something. Okay. All right. Fine. That's a left eigenvector. These will all get clear, hopefully, soon. All right. So these are eigenvectors. Now, if V is an eigenvector of A with an eigenvalue lambda, then so is, yeah, obviously you can multiply it. That's fine. Now, even when A is real, the eigenvalues can be complex. They have to occur in conjugate pairs in this case. And the eigenvector can also, of course, be complex. And in fact, if the eigenvector is real, then lambda has to be real because A times V is real. And that's got to be lambda V. So it doesn't work unless lambda is real. Now, when A and lambda are real, you can always find a real eigenvector associated with lambda. So you don't need to... Of course, you can also find complex eigenvectors associated with a certain eigenvalue. And we've already talked about that. There's conjugate symmetry. But there's more you can say about that. You can say the following. If A is real and V is an eigenvector associated with lambda, then its conjugate is an eigenvector associated with lambda bar. That means roughly if you find one eigenvector, one that's complex, the truth is you really just got two, in a sense. You just got two, because you could conjugate that eigenvector, and it would also be an eigenvector of A. The conjugate would be an eigenvector of A. It would be associated with the eigenvalue lambda bar. Okay, and we're going to assume A is real, although it's not hard to change the things we talked, to modify this to handle the case when A is complex. All right, so there's a question. Sorry, how do I define what? Oh, the conjugate of a vector. I'm sorry, let me explain that. So a conjugate, of course, of a complex number. What do you think? Should I switch to I like right now? Yeah, let's do it. That J stuff that's weird. Okay, there's a complex number, and its conjugate is actually this. Okay, looks like that. So vector is just the conjugate applied term by term. But actually, I'm glad you brought that up, because there's something called the Hermitian conjugate of a vector, and that does two things. It transposes and it conjugates. And that's often written this way, V star, that's one way. You will also say VH, like that. And you will also see this, and I disapprove. But anyway, this is the notation in MATLAB. So in MATLAB, watch out. Prime, which up till now has meant transpose, in the case of a complex vector or matrix, is actually going to also take the conjugate, and that's called the Hermitian conjugate. So just a little warning there, right? So you can, that's what this is. Okay, so that's the conjugate. Okay, so let's look at the scaling interpretation. I think that was the one interpretation I heard. It's something like this. We're going to take lambda to be real. So if V is an eigenvector, the effect of A is very simple, just scaling. Okay, I mean, you know, sure, AV equals lambda V. And so the picture would be something like this. You know, here's a vector X, and then here's AX. You know, unrelated. But, you know, here's an eigenvector, and AV comes out in the same, on the same line. By the way, what's lambda for this picture? Negative what? Let's see, negative what? 2 point something? Never, I don't know. I don't know what it is. It's negative 2.3. I don't know. It's something like that, right? Okay. So, by the way, this is the interpretation given normally if you take a math class, and the only one. Now, of course, it sort of begs the question, like, basically, who cares? I mean, so what if you multiply a matrix by a vector? Well, you can imagine cases where it would have some interesting applications, but anyway. Okay, so that's what it says. It says you have an eigenvector, the effect, it's a special vector for which the effect of A on it is very simple. It just scales. So actually, I say something like all the components, you know, get magnified by the same amount, something like that. Okay. And you can say some obvious things here. For lambda, if lambda is real, if it's positive, it says that v and av point in the same direction. If lambda is real and it's negative, they point in opposite directions. That's like our example here. If the eigenvalue has magnitude less than 1, AV is smaller than V, and so on. And we'll see later how this is related to stability of discrete time systems, actually all of these things. But now here's the real interpretation of an eigenvector. This is it. It's this. Let's take an eigenvector. So AV is lambda V. V is non-zero. And let's take x dot equals A of x, and let's say the initial condition is V. So let's start a linear dynamical system, autonomous, at an eigenvector. Okay? Then the claim is this. The solution is embarrassingly simple. It is simply, that's a constant vector V. You stay on V, and all that happens is you either grow or you shrink with time, and each one exponentially. Very simple solution. Lots of ways to see it. Here's one. We could say, well, look, x of t is e to the TAV. E to the TA, I write it as the power series. This is slang, of course, matrix divided by scalar. And then we multiply that out. We say, well, I times V, that's V. TAV, now AV is lambda V, so I write it this way. If AV is lambda V, then what is A squared V? What am I doing? My God. Okay, A squared is A times AV, which is this. AV is A times lambda V. The lambda pops outside. You get lambda times AV. I reassociate, and I get lambda squared AV. There we go. Okay? So, you don't like what I did? Oh, the A goes away? Good. Good. Thank you. Your credibility is slowly growing, actually. That's good. That's fun. Okay. Good. That's what you should be doing. All right. Of course, it'd help if I wrote it legibly, but I think this, I don't know, this just makes it more of a challenge. That's good. It means you really have to be watching. Okay. So if you look at this thing, these are now all scalars multiplied by V, and if you pull the V out on the right, you get a scalar here, but that scalar is the power series for e to the lambda V. Okay? So that's it. So now, this is really, in fact, what an eigenvector is. An eigenvector is an initial condition for x dot equals ax, for which the resulting trajectory is amazingly simple. If it's a real eigenvector, it stays on a line. It just grows if it's positive, shrinks if it's negative, stays where it is if it's 0. So that's it. Now, if lambda is complex, right, we'll interpret that, we'll get to that later because it's a separate case. So what it says is if you start in an eigenvector, the resulting motion is incredibly simple. It's always on the line spanned by V. And that's actually called a mode of the system. So that's what you call that, is a mode. And it's a word. This is a word that's used kind of vaguely and in lots of different areas, but that's what it is. It means it's a really simple solution. Okay, so this brings us to a topic that's related to this, which is very interesting. It's the idea of an invariant set. So if you have a subset in Rn, you say it's invariant under x dot equals ax. If whenever you're in it at time t, you will be in it forever after. Okay, so that's what it says. And the picture is something like this. You have a set like that, and it basically says if these are the trajectories of x dot equals ax, what you're allowed to do is you can cut into the set, but you can't exit. That's what it means to be invariant. Okay? So that's the picture. It may not look this clean because often S is something simple. Let me ask you a question. Could you ever have an invariant set that is a single point called x0? What would it mean to have a single point that is an invariant set? What is it? That's exactly what it is. That's a very pedantic way of saying you're in the null space. Let's check if that's right. It's an equilibrium point. It's a point for which, if you're in there, well, you can't go anywhere. If you can only be one point, it means you're constant, therefore your derivative is 0. and therefore it just means AX equals 0, right? So basically, this is sort of if and only if X0 is in the null space of A. Those are the equilibrium points. That's just that's a silly example, but so this is the idea. By the way, the idea of an invariant set, unlike the idea of stability, which is actually really only of conceptual help, whatever that means, conceptual use. The idea of invariant sets is extremely useful in practice. It's amazingly useful. It's real, and actually not many people know this or appreciate it. That's real. Because if I say, I just designed the altitude hold control system on a 747, and if your initial altitude is between plus, if I give you a box that's real that says from 29,500 feet to 30,500 feet, I give you a box on other things involving things like your pitch rate and all sorts of other stuff, and I say, that box is invariant, that is extremely useful and very practical. It says basically, if you start in that box, you might start in that box because it's a big downburst of wind. It says if you start in that box, you're going to go settle back up to your equilibrium point without leaving it. That's really useful. It's quantitative and everything else. So I just comment on that. Okay, that's the idea of an invariant set. Well, we just saw one. If you have an eigenvector, what we just found is that the line is invariant, and that's kind of obvious. It basically says if you're here, an x dot, if lambda is positive, it means if you start here, you actually go along along the line. And in fact, you can even say the ray is invariant. So if you start in the positive part, it's invariant. And if lambda is negative, it basically says you're going to be on this line segment between here and here, because you start at this point, and all that happens is you decay. You can't get out. By the way, can you enter this set? Actually, we haven't got there yet, but you can't. You can neither enter nor leave it. A set like this. So, but anyway, it's invariant. Okay. Now we can talk about complex eigenvectors, because the best way to understand it is with invariant sets. So let's suppose you have AV equals lambda V, V is non-zero, and lambda is so you have a complex eigenvector. Well, then we have A e to the lambda t. For any complex number A, that is a complex solution of x dot equals AX. Now, typically, when someone says, we're looking at x dot equals AX, A is real, we're only interested in real solutions of x dot equals AX. So typically, you're only interested in that. Nevertheless, for what it's worth, that thing, A e to the lambda t v, is a complex solution of x dot equals AX. But that means that actually both its real and its imaginary part separately are solutions. All right? So let's look at the real part. X of t is the real part of A e to the lambda t times v. And now we're going to do this very carefully here. E to the lambda t, I'm going to pull out the e to the real part, e to the sigma t. Sigma is the real part. Here, sigma is the real part of lambda. I'm going to pull that out in front. And I'm going to write the rest of this thing out this way. Of course, there's a cosine t and a sine t and so on in there. And you get this expression in terms of alpha and beta, where alpha and beta are the components, the real and imaginary components of A. So, and you could just multiply this out and check me. But the point is now you should actually see some things here that you recognize. That's just some vector that depends on this A. That's any old vector there. This matrix should be a friend of yours by now. That's a rotation matrix with angular velocity omega. So it takes this vector in R2 and it rotates it. Okay, I'm not sure which way it rotates, but it doesn't matter. It's one way or the other it rotates with an angular velocity of omega radians per second. So this takes your initial vector and it rotates it. This says you get two numbers, and those are the two numbers that you mix the real and the imaginary parts of that eigenvector with. So you form a real and imaginary part, and then we can add the growth factor later. You can put the growth factor anywhere you like. It's a scalar. So that's it. And we see the most amazing thing. We see the following. It says that if you have AV equals lambda V, where where lambda is complex, V is complex, it says the following. It says basically says you stay in the plane, and now I'm talking about real solutions. The real solutions stay in the plane spanned by the real and imaginary parts of that eigenvector. That's what it says. Okay, so when you get a complex eigenvalue, you get a complex eigenvector, you look at the real and the imaginary parts. Those are two vectors in Rn. They span a plane. Oh, let me just ask one question here. What if they were dependent? How do I know it spans a plane? Ooh, that's a good question. Let's answer it. I'm just saying these two vectors are, one is not a multiple of the other, right? That's what it means for it to span. What? Well, I don't know. Let's see. I mean, let's just say, suppose Vm were the same as V real. So the real and imaginary parts of the eigenvector are the same. What does that mean? Is there a law against that?
You can just have a reverse eigenvector.
Precisely. So let's suppose the imaginary and the real parts are just, they're equal, right? And you say, ha, there's no plane here. You got two vectors, but they're in the same line. They span a line. Okay? Or as you might say now, pedantically, that n by 2 matrix there, it's not full rank. Okay, so what happens in that, if this is equal to that, you would say, well, wait a minute then. The eigenvector is really, it's V re times 1 plus I. There, see, I made the switch. Well, on the page I have J, so I'll switch it to J. There, looks like that. If that's the eigenvector, so is that. And it says that the real eigenvector alone is an eigenvector. And that says that lambda is real. By the way, which is not contradicted here. So I should say something like not real, like that. So to be technically right, but it's okay, it's fine. Okay, so what happens, so now here, sigma gives you the logarithmic growth or decay factor, and omega gives the angular velocity of the rotation in the plane. So now you should be getting you want a picture of this. So basically, you have x dot equals ax, a complex eigenvector, a real eigenvector that's easy. It's a direction where if you start the system anywhere along that line, it will stay along that line. A complex eigenvector, you look at the real and imaginary parts, that spans a plane in Rn. And it says if you start anywhere on that plane, you will stay, number one, you'll stay on the plane, but the motion in the plane is very roughly kind of simple. Basically, it rotates on that plane with an angular velocity of omega. That's the imaginary part of the eigenvalue. As well, it grows or shrinks depending on the real part of the eigenvalue. That's what it means. Okay, so we're going to look at some examples and stuff, and so will you, separately. So, all right. Now let's look at the dynamic interpretation of left eigenvectors. So here, suppose W transpose A is lambda W transpose, and W is non-zero. Then let's look at DDT. Let's let any solution of, let's look at this. DDT of W transpose X, let's let X dot equal AX. But now X is any solution. It's not started from an eigenvalue, eigenvector, nothing. Just any solution. If I look at DDT of W transpose X, I get W transpose X dot. But X dot is AX. I get W transpose AX, but W transpose A is lambda. So I get this. If you look at the beginning, if you just get rid of this, you see that is W transpose X satisfies a scalar differential equation. And therefore, linear differential equation. Therefore, the solution is this. Okay? Now, what this says is really cool. It says that a left eigenvector gives you the coefficients in a recipe or a mixture, because that's what a row, that's what W transpose is. W transpose is a linear function, a scalar valued linear function of X. It's called linear functional of X. So it's W transpose X. And it says if you get those coefficients just right, this thing will undergo a very, very simple motion. Even if X is going crazy, if X is in R 100 by 100, there's 100 eigenvalues, all sorts of crazy motions and modes and growths and oscillations going on. W transpose X will have only the pure lambda e to the lambda t component in it. Okay? So, and you can say lots of cool things now. Now, here's something of actual use. It's this. If lambda is an R and lambda is negative, then the half space, the set of Z such that W transpose Z is less than A, is invariant. Okay? The reason is this. Because W transpose Z does not, it just decreases. That's all it does with time. Now, if you decrease, it says basically something, so let's draw a picture. It basically says that if W points this direction, it says that if you, and lambda is negative, and W transpose A equals lambda W transpose like that, it says basically the following. It says if you start here, by the way, in the general case, here, this region is a strip. You'd call this a strip in R2. In Rn, you would call it a slab. Okay, so that's basically this is a half space. It's everything in between two parallel planes. Hyperplanes is a slab. So what it says is that in the general case, this slab is invariant. What it says is if you start in that slab, and by the way, now you can enter a slab. If you start in the slab, you will stay there forever. That's what it says. In fact, what it says is actually quite interesting. It says that in this case in 2 dimensions, it says that when if you start here and I draw whatever the trajectory is, I can tell you this. If you only look at its sort of component in this direction, that is just nicely exponentially decaying to 0. Now, by the way, this thing can be shooting off to the left or right, or going to 0. All sorts of crazy stuff can happen in that slab. But sort of if you look at the slab coordinate, that's this thing, it's just very happily decaying. So that's the picture. And this is already something very useful. This is already useful. It tells you there's an invariant, you get an invariant slab or half space, tells you if you're in there, you keep going. Okay. Hey, Jacob, make a note. Let's construct a problem out of that. We'll edit that out of the. Actually, it looks like I'm not going to be able to edit these videos. It's too bad. I could get rid of things like that. Maybe I'll figure out a way. Okay. Okay. Now, if you have a left eigenvector corresponding to a complex eigenvalue, then it says that both the real and imaginary parts of W transpose X, it gives you 2 planes, and they both have these a sinusoid. Okay, so now let me give a summary. By the way, it's examples that will kind of make all this clear. So here's the summary. A right eigenvector, that's a very special initial condition in a linear dynamical system. That's what it means. It's a point for which if you start the system there, you will get a very simple motion. Either a decaying exponential, a growing exponential, or a exponentially growing or decaying sinusoid. Period. That's it. Well, yeah, we'll leave it that way. That's what a right eigenvector is. And by the way, if you just pick a random point and then look at the solution of x naught equals ax, you're going to see everything in it. You'll see all the modes, all the frequencies, and everything. You'll get a very complex behavior. Okay. A left eigenvector has nothing to do with initial conditions. It's a recipe. It says if in a left eigenvector, it says that if you form a certain, if you take any trajectory of the system. Now, in general, a trajectory system is going to have all the modes, all the frequencies in it, all sorts of oscillations, growth, decays, all added together. This says if you make very special linear combinations of the states, and those combinations are given by left eigenvectors, then what looks like a fantastically complicated trace or trajectory will just simplify. And you'll be looking right at something real simple, a decaying exponential or a growing exponential or a sinusoid or something like that. That's what a left eigenvector is. Okay. So they're different. It's actually very important to understand which is what they are, and that'll also come. Let's see. Okay, let's do this. All right, so let's look at an example. It's a stupid example. It's simple. It's x dot equals -1, -10, 10, 1, 0, 0, I don't know, whatever. Now, all these 1s and 0s, you should have an overwhelming urge to draw a block diagram. So this is the block diagram. uncontrollable urge to try. That's it. So you see, that's a chain of integrators. By the way, the chain of integrators in here corresponds to the ones on the lower triangle, which corresponds to a up or downshift, one or the other, or something like that. It's upshift, yeah, something, whatever it is. Downshift? It's a downshift in this case. Okay, it's a downshift. So you get the chain of integrators, then these numbers here go in here like that. Okay, well, let's look at the eigenvalues. Well, it's easy, by the way, matrices like this that have a kind of a lowered, ones on the lower diagonal, and then a row that's non-zero. They're called companion matrices. And there's a bunch of different kinds. You can put this row here, you can put it at the bottom. That's called a top companion matrix, and you have a bottom companion matrix. You could have a left or a right, and it goes on and on. And I guess in a classical course like this, you would be tortured possibly for up to a week on just companion matrices. I have no idea why, but this would be the case. Just to let you know. Okay, so that's a companion matrix. And the cool thing about them is it's extremely easy to work out the characteristic polynomial. Well, it makes sense. A lot of zeros and ones there. That's on your side, and so on. So actually, it usually turns out the coefficients are these guys up in the top. But it's better, since I never remember what it is, I just work it out myself. So basically, you have to work out the determinant of this. 10, 10, that's minus 1, 0, 0, 0, minus 1, 0. And you have to calculate that determinant, except I should put some s's here. There we go. And I don't know, you can start wherever you like. You can start with it's s plus 1 times the determinant of this thing. There's a 0 there which saves you from at least one of the terms. So, and you just get an s squared. And then you say minus 10 times the determinant of, I guess what, you cross, how does it work? You cross this and this out. The determinant of that, again, there's a couple of zeros there, saving you at least one multiplier or something. And you get the s. And then you get plus 10 times the determinant of that. And once again, the determinant is 1 or something like that. So these are not bad. I mean, that's about my speed. That's about 3 or 4 floating point operations. That's about the number I can do without making a mistake. So I don't recommend doing more than that by yourself. So, okay, so that's the characteristic polynomial. And we just factor that, and that's s plus 1 times s squared plus 10. So the eigenvalues are minus 1 and plus minus j times square root 10. Okay, these correspond to these. Now, by the way, immediately you should know what to expect. You should know that when we look at the solutions of this third order linear autonomous dynamical system, you should see things that look like e to the minus t, and you should see pure sinusoids which look like cosine squared 10t and sine cosine 10t, that kind of thing. If you see anything else, if you see a growing exponential, you see anything with like a growing like t or something, it's wrong. It can't be. So immediately when you see this, you should be primed for what you're gonna see when you run a solution of this. Let me say a couple more things. There is no one, as far as I know, who can look at a matrix and kind of look at the eigenvalues. I can tell you have a feel for the eigenvalues. 2 by 2, no problem. That can be learned. Maybe 3 by 3. Actually, that's not true. No, not even. This one, I could fake it because I know it's a companion one. I could quietly factor that in my head, and if I distracted other people, it could look like I looked at that and go, yeah, well, you're going to get some oscillations. Or I think some oscillations. Yeah. They're going to be around, I'd say on the order of about 3 is my feeling is going to be the 3 radians per second. The period's going to be around 1, 2, I mean, something like that. You could do that. And someone say, that's amazing, how'd you do that? And you go, well, yeah, it's just, you work with these enough. And you see the minus 10 here? That kind of, see when x2 is going up and x3 is going down, these kind of cancel. And then the minus 1 here, that kind of goes around. This is complete nonsense. Actually, what I'm saying is that while it's entirely reasonable if someone walks up to you in the street and says, you have y equals ax, you look at y for 10 seconds, you should have, I mean, there's some details you won't know, but things like, if there's zeros in that matrix, you have a rough idea of what doesn't depend on what. If you see huge entries, negatives, positives, you should know, no excuses. Okay? X naught equals AX, this is wrong. There's no one who can look at A and say that's good. I mean, there's special cases, but you can't. That's in general, and that's actually an interesting thing because it means it's not obvious. There's no one who can look at one of these things, and all this is, if you think about what X naught equals AX is, it's not much. It's basically a bank of integrators. The outputs come out and they run through a matrix, which kind of blends everything around, and they get plugged back into the integrators. How hard can it be to understand what that does? Anyway, the answer is, it's really hard. Well, I mean, it's not. Once you know about eigenvectors, eigenvalues, matrix exponentials, it's not hard. But the point is, you don't know about those things, there's absolutely no way you will have a clue what happens to a system here. So you can't look at something and say, here's how it works. Here's my model of my economy. And you have a 5 by 5 matrix. I mean, with 5 sectors in the economy. That is tiny. You cannot look at that and say, wow, we're going to have some business cycles. I'm also seeing some pretty, I'd say we're going to get an overall growth rate around 5–6%. Nobody can do that. Nobody can look at 25 numbers and tell you that. I just want to emphasize this, right? It's like least squares. You can't do least squares in your head. Good thing you don't have to, but still. I'm not sure why I'm telling you this, but it's probably important to say. I don't know why it's important, but it seems like it's important. Okay, all right, back to this thing. So here we are. We are expecting decaying exponentials, and we're expecting oscillations with a period of 2. That is to say, if you followed my intuitive argument about how all the interactions came in, and then the signal, you could, if you want to explain an oscillation, you could say something, oh yeah, no, I can see it, because it kind of goes like, but then it comes around again and again and again. It takes about 2 seconds to go around, so that's how you do this. Okay. All right. So here's just some initial condition we selected. Here's the solution. Maybe I'll actually say something real quick. You'll be doing this, and there's some things I should mention. I think I mentioned last time. I'll mention it again. It's very important. Please, please, please don't be don't be a victim of this. In MATLAB, and indeed in several other higher level languages, if you write exp of a matrix, you're going to get it element-wise. Okay, I don't know what that is, but it is nothing that has anything to do with the matrix exponential. And actually, for that matter, exp of A works if A is non-square. Okay, and that would be true in lots and lots of languages, higher level constructs. Okay, you have to say exp M of A, and I guess that's the matrix exponential to actually get the matrix exponential. You try exp M of A with A non-square, and you will I hope, pray. I know that you will get a stern warning about what can be matrix exponentiated. Okay, so to make a plot like this, it's the easiest thing in the world. You could actually even just do this. There's absolutely no harm in writing out stuff like this times x0 or something. There's just no harm in that. And then putting a for loop around this or whatever you like. None. No dishonor. Nothing. There's faster ways to do it and so on. By the way, there are some built-in ways to actually find the solution of a linear differential equation. I actually do not recommend that you use them. Okay. One of them, they've got stupid names like initial. That's supposed to be like an initial condition problem or something like that. And God only knows. It's like x and a0. Unless you know about these, don't use them. Because this one, you look at it, you know exactly what it does, and there's no mysteries. And this isn't just some stupid, some guy sitting in wherever they are in Massachusetts decided what to do in some cases here. In this case, it's transparent. You know exactly what's going on. So that's what I recommend. So that was just a weird aside. I don't use these. I think some of our solutions, maybe even some of the exercises, may have some old references to this. Ignore them. So we'll clean those out. All right. I mentioned this just in case you're curious how I created this plot. That's how I did it. All right, back to the story. So this shows you x1, x2, and x3 versus time. Everything is consistent. We don't see any growing exponentials. In the first one, you see mostly just a sinusoid. And sure enough, let's see what the period is. Hey, wow, my intuition was excellent. So my intuition was that the period would be around 2, and indeed it is around 2. You don't see a decaying exponential in here too much. This one, there is a decaying exponential, but I guess it's kind of going up towards 0. That's fine. It's just got a negative term in front of it. And here, in the third component of x, you see more of the decaying exponential and less of these things. By the way, just for fun, there is something you can see here. x1 is quite wiggly. x2 is less wiggly, and x3 is less wiggly still. And want to see if you're going to go for this. It's kind of cool. So x1, what happens is these things repeatedly go through integrators. That's what happens. And so when you push something through an integrator, it gets less wiggly. So that's why you'd expect, let's see if I can get this right, x3 should be the least wiggly because it just came through 3 integrators. x2 should be more wiggly, and x1 most wiggly. You buying it? No? Why not? Did I make the opposite conclusion? Sometimes you make an excellent interpretation that supports the opposite conclusion. What you should do how come you're not buying it? Well, didn't you understand my explanation before about how x2 and x3 come out and then they interact? They kind of cancel, and then they slosh around like every 2. I thought that was pretty clear, okay? I don't know. I thought it was clear. Now, come on. If you integrate a signal, it gets less wiggly.
Why is the intuition behind it?
Oh, between integrating a signal and it gets less wiggly? Oh. Well. No, let's just do it. That's fine. No problem there. Are you in electrical engineering? Knew it. Cool. Okay. So it's okay. Let's just do it. Here's a signal. Ready? Here's this signal. What's the running integral of that guy look like? Well, why did I make it so complicated? Anyway, it doesn't matter. I don't know. So look, the point is, these things that kind of go up and down as you integrate, you're sort of averaging everything up to that point. And so the running integral of this thing is something much smooth. It's much smoother. It kind of, I don't know what it does, but it kind of goes down a little bit. And I'm making this up, totally making this up, just for the record. There you go. Okay, it looks like that. So, buying it now? Yeah, and that is exactly the integral of that, by the way. But I'll just anyway. That, by the way, that's not easy to do. You have to train for a long time to be able to do hand integrations like that in real time, under pressure. And you'll see it's dead on if you check. Okay. All right. All right. Let's look at a couple of things here. Let's do the following. Let's take the left eigenvector associated with the eigenvalue -1. Well, that's this. It's G. It turns out to be 0.101. That's the left eigenvector. And before we do anything, you have to interpret what this means. This eigenvector, what this is telling you a recipe. That's what it's saying. This says if you were to mix 0.1 of x of t, 0.1 of x1 of t, with 1 of x3 of t, if you were to add those two together, what will come out will be pure exponential. Okay? Which is to say, it's a filter. It gets rid of the oscillatory component. Just gets rid of it. And indeed, it looks like that. And really, I swear, the source code that generated this figure really does do this. I could have just drawn an exponential, but anyway, I didn't. I mean, probably the source code really does this. And there it is. You see, if you take 10% of the first component, add it to the last, all oscillation goes away, and you get a pure decaying sinusoid. Let's see if we can eyeball that. 10% of this. All right, so do that in your head. That gets scrunched. This gets scrunched way down to kind of a small oscillation like that. And then it says, apparently you add it to this. And, oh yeah, I'm seeing it. I am sort of seeing it, right? Because look, see, they're almost like anti-phase, right? That's kind of up here when that's down there. So anyway, never argue with a left eigenvector. It's right. You can see that's what it does. So if you scale this down, add it to that, oscillation goes away, and you're left. In fact, you would say that the English description of this is you'd say By multiplying by g, or forming this weights, you have, let's see, what would you say? Forgot the word now. It was a good one. It was really a nice one. I guess you have filtered out, or you have brought out the exponential or something like that. That's what you've done. You've filtered out the sinusoid. You have revealed the exponential. I don't know, something like that. Okay. So that's a left eigenvector. Now let's look at the eigenvector associated with this eigenvalue. Now that eigenvector says it's complex. Has to be, because that's pure complex. Now what that says is the following. There's an invariant plane that's spanned by these two vectors like that. And it basically says if you start on that plane, now this is an R3, so you're actually going to, in fact, I'm going to ask you to visualize this. In fact, let's do that. Let's take R3, so you should be looking at R3, make a plane going through it. That's spanned by these two. You don't have to get the angle right, just put some stupid plane through it in your mind. Okay, in R3. Basically, it says if you start in that plane, the motion is really simple. First of all, you stay on the plane. So imagine this tilted plane, an initial condition. Actually, in this case, because it's pure imaginary, you just oscillate. Everybody got that? And every roughly 2 seconds, you come around. You stay on that plane. Now, if you're off the plane, what happens? Now you have that decaying exponential. So the decaying exponential, in fact, well, we'll get to that in a minute, but that's the point. Oh, by the way, this g, that happens to be the outward normal of this plane. And you can check me. If you multiply g transpose times that, you get 0. G transpose times that, you get 0. And you know what that means? It means g is the normal to this plane. Okay? So now I think we can do the visualization exercise. Yeah, let's do it. Here we go. You ready? So you start like this. Take R3, picture a plane. Okay. Now in that plane, if you start in that plane, your trajectory is beautiful. It just undergoes a perfect, it's not a circle, it's an ellipse in that plane. So it just oscillates. Everybody got this? Okay. Now we're going to do the following. The normal to that plane actually is the left eigenvector associated with -1. Okay? So that means, take that plane, if you're off that plane, and if you actually just study your height above or below that plane, that's g transpose z. That simply goes down as an exponential. Okay? So I can see this is, no one gets anything. Okay, so we're going to try it. So now we're going to throw it all together, and I think we have a perfect visualization of the whole thing. There we go. You have your plane. If you're on that plane, you oscillate. Okay? If you're off the plane, then your height above or below the plane simply goes like a negative exponential, e to the minus t, and you head towards that plane. So if this is the plane and you start up here, by the way, you're rotating the entire time like this. So you're rotating same angular speed, but what's happening is your height above that plane is exponentially decreasing. So the solutions look like this. That's never going to come out in the camera. And it doesn't, in fact, I don't even understand. No, is this making any sense? You start below the plane, you wind in the same direction, but you wind up to the plane. And so, in fact, what would you call this linear dynamical system? It's got a name. It's an oscillator. And basically, when it starts up, after 5 seconds, if that's what the units of t is, you're on that plane and oscillating. It's an oscillator. And in fact, you'd refer to that first bit, the first part when you're zooming into that plane or up, that's called the startup dynamics of your oscillator. That's the way it works. Everybody got the picture? So, and that's it. And the normal is the left eigenvector and so on and so forth. So that's the picture. Well, here's an example just showing that it actually works. If you take x of 0, if you start in this real thing and then propagate the solution, you indeed get an oscillation. I mean, we knew that. So that's the picture. Okay. So that's the idea. Okay. We'll look at one more example, and then we'll move on. By the way, this mystery about the left and the right eigenvectors and how they're connected and weirdly one is orthogonal to the other, we're going to get to all of that later. By the way, it's related to this mystery involving, which isn't a mystery. It's a mystery involving the rows and columns of inverses or something like that. So, in fact, let me go back to that because we're going to need that, and we'll skip on. I want to talk about this. If you have a matrix, if I take V1 up to Vn, actually I won't take these because that always in the context of eigenvalues, those sound like eigenvectors, so I won't use those. Instead, I'll call them T1 through Tn. And I'm going to make these are independent vectors. Okay? And if you take the inverse of this, and I call the rows, S1 transpose down to Sn transpose like that, okay? Then, I don't know if you remember, but we called these S's, that's the rows of the inverse matrix, right, which was formed by concatenating a bunch of columns. We called this the dual basis here. And actually, you remember what the interpretation of the S's are. It says that when you express a vector in the T expansion, S3, for example, is the thing that tells you the recipe. It tells you how much of T3 to put into your recipe to recover your vector X. That's what it does. So that's what these S's are. And then we found out this. Si transpose Tj is equal to what? It's not complicated. I mean, it looks mysterious and complicated, but it's not. Basically, this thing, if I take this matrix, if I plug in on the left here, T1 up to Tn, I'll insert it there, and I'll put T1 up to Tn here. What's the right-hand side? That's I. And now, if I take this matrix written out by rows and another matrix written out by columns, and I multiply them, I get I. But there's a very simple way to interpret a matrix viewed as rows multiplied by a matrix viewed by columns. It's basically, it calculates all, the 1-1 entry, for example, of this product is S1 transpose T1. So what's S1 transpose T1? It's 1. What's S1 transpose T2? Precisely. This is delta Ij. Okay? So that's the idea. So, and these are called dual bases and things like that. And it looks, I mean, when you first encounter it, it looks like it's kind of mystical, this strange thing that, like, and you have to be very careful, right? Because I am not, absolutely not saying that the SIs are orthogonal. What do you know about this or this? Absolutely nothing whatsoever. Okay? So it's this weird thing where the S's are orthogonal to the other T's. The T's are orthogonal to the other S's. So there's this weird thing where one group is orthogonal. Anyway, it's this. It's just that. Okay. So we're actually going to find out that the left and the right eigenvectors satisfy exactly the same relation. So but we'll get to that next time. And we'll quit here.